Grrr. Welcome to Balance or Bust. So, we're going to do some more practice of our 5 types of reactions. Again, there's many more, but these are 5 that you're going to be able to do. And here's Leo, our inspiration. He's here to help. And the Red Ox, they'll get some action. All right, so first type we've actually been doing for over a month. And that is a combination. So a metal and burning means oxygen. So the non-metal is oxygen. So our equation, we write our reactants, magnesium plus oxygen. Now, pretty sure very first question says, what are your diatomics? So let's review them. There's 7 diatomics, and they do make a 7 on the periodic table. Well, kind of, sort of. So there's nitrogen and oxygen, and fluorine, chlorine. There's probably beautiful songs somebody could write. Bromine and iodine. So the halogens, remember Acetine, can't look at her, and hydrogen. They are diatomics when they are by themselves, which does happen in several of these, especially in combos. And notice they are non-metals. All right, so magnesium and oxygen burn, so we show an arrow. It's a chemistry way of showing an equal sign. And we make an ionic compound. Now, there are some where you'll have a non-metal and a non-metal. In that case, I will have to tell you what happens. And there's a reason Leo's wearing goggles, because we can do some demos here. All right, so they're going to combine, and you don't want to just combine them and put a 2 down here. We want to respect charges. Whenever we combine, or whenever we write a formula for a metal and a non-metal, we want to write their charges, which Leo will tell us is oxidation numbers. That was a little red ox. Oops. Little red ox has only 3 legs. I dropped him. Not today, a couple years ago. But she's always got a smile. And a little rainbow. Boo. All right. So, again, write your reactants. So reactants. And this is where you do subscripts. So we talked about this, right? So diatomics, if they're alone. And the other thing we look at is the subscripts to balance the charge. You don't really have to write that down. We've been doing this. We're just now putting all of it together. So since they have the same charge, when your metal and non-metal have equal but opposite charges, we don't need a subscript. Now, back when we were doing this initially with the cat and the onion, I told you had to erase your charges. Final answer can't have charges. But again, with these, we can keep the charges as long as they're up above, so I'm not getting confused and you're not getting confused, because we're going to use them for the Leo Gur. But let's go through our 5 types of reactions, and then we can go back and do Leo Gur. All right, we have to, so you get your reactants. You figure out what type of reaction it is. So if it's a metal plus a non-metal, so reaction type is our second step. And then you do your products, and that's where you do your subscripts, which we don't need them for this one. And then we balance. And that's where the coefficients come from, or the coefficient. So we have 2 oxygens over there, so we're going to need 2 coefficient here. That gives us double magnesium, so we put a 2 here. And I like to use the lines. The oxygen, no. But if you want to put a 1 in front of it, I won't mark you wrong. All right, so we're good. Next type, decomp. And you're going to know because it's always going to tell you decomposes. It might say it breaks down, but the key with a decomp, whoops, let's finish up here. You're going to have a metal plus a non-metal. Now, there's other types of combos. Again, more complicated ones I will have to tell you, but the key with a combo is there's one product. You've combined everything. Online, they usually call these synthesis, and we're going to call them combos. Decomps, there's one reactant. So on combos, there was one product. I don't like the name synthesis because there's many other things you can synthesize that are not combo reactions. All right, so ammonium dichromate. This is just a cool reaction demo. These two go together. So let's do it. Ammonium dichromate, I gave you the formula. NH4. So ammonium is a +1 charge. So ammonium and then dichromate, Cr2O7. Now, for those who will be with me in 221, in 221 we add states of matter. In this class, we're not going to worry about it. We're going to get the idea of putting them together. All right, so a more complicated one like that I would give you in here. We lost our black pen. There it is. We want to keep our diatomics always looking at us so we know not to forget them. And I tell you, with a decomposition, they have to have been, the experiment has to have been done. These goggles are really tight. So it makes nitrogen, comma, so that means plus water. I assume you know the formula for water, H2O. And then chromium 3 does not mean you have 3 chromiums. It means chromium has a +3 charge. So chromium 3 oxide. So we have to do charges, and the charges tell us our subscripts. So we have a 2 and a 3. So now we have to balance. Now, again, there's all these really cool videos that teach you how to make a chart and you balance back and forth, and I used to teach that way. And what I found is the students who did that would take a half hour to balance one equation. So you can do it that way, but it really, it's not that efficient. You guys can do this. So, nitrogen. There are 2 nitrogens, because that parentheses, we double everything inside. And over here, I have 2 nitrogens, so we're good. Hydrogen, 4 times 2, parentheses. So 4 in front of the H2O, because that will give me 4 times 2. Don't worry about the oxygen, we're going to get there. All right, it's like where you say a prayer and hope it all worked out. 2 chromiums, and here I have 4 oxygens, and then I have 3 more. So 4 plus 3, 7. And we have 7. That prayer worked. Imagine that. All right, let's do a demo. You ready? So, we'll see if I can videotape a little bit better. We have a pumpkin, because it's Halloween time. And we need to light a Bunsen burner. All right. Just relax. We're going to turn the other way. All right, we'll move our pumpkin. There's another pumpkin for the next demo. So, oh no! So this is our piece of magnesium ribbon, and those of you who are Boy Scouts, you've burned magnesium ribbon. And any of you have seen fireworks? You've seen magnesium is a bright white one that then you like see spots, because that's what happens. I'm going to turn the lights off for this one. That bright orange powder, crystals, that's ammonium chromate. So all I'm going to do is light the magnesium ribbon on fire. Here we go. Shouldn't look at it. And then, oh, you gotta turn it back on. Here we go. It was supposed to be coming out of the pumpkin, but I couldn't find the light. We can still put the pumpkin on here. Oh, we're going to catch the paper on fire. That's good, because combustion's the next one. Find some water. Put the fire out. There we go. So, what's that powdery green stuff? Can you see it? I'm trying to see. Yeah. It's the color of money. It's what our country used. I don't know if they still use it, but they used to use chromium-3 oxide to color money. I got a whole bunch here. It's a little warm right now because this was an exothermic reaction. All right, but that's what happened. The nitrogen became part of the nitrogen in the air. The water vapor became part of the water vapor in the air. So initially we used a combo. A lot of heat was generated and it ignited the ammonium dichromate. So the ammonium dichromate is not very stable, but it needs something to kick it into action. And it's not stable because if we went through figuring out all our oxidation numbers, this chromium has a +6 oxidation numbers. Everybody else has their typical ones, so nitrogen has a -3, hydrogen's 1, but the chromium +6 is a really large number. And, all right, it's a decomposition because it's something that breaks apart, and again, I'll tell you what it starts with. This is a complicated one, but I like to show it because, you know, it was a fun demo to do, especially with Halloween. Just before. See if the smoke doesn't happen. This is always on Halloween week. All right, combustion. Combustion means burn. Burn, baby, burn. And so I will give you the formula. Those of you who will be with me in organic chemistry, Chem 105, you can become great at these. Because methane is 1 carbon, and that's natural gas. So that Bunsen burner that was going, that was natural gas. And it burns, which means plus O2. So you either love combustions or you have a little bit of an attitude. You're going to all love it because it always means whatever I gave you plus oxygen. Burn. And we assume it works perfect. The carbon and the hydrogen are each, the oxygen's really greedy right now because the oxygen wants to be -2. And right now, by itself, it gets a little halo, a 0. It doesn't like being 0. So it combines with everything. So it combines with carbon, and the stablest thing it can make with carbon is CO2. That's the whole thing that's going on. And it combines with water, it combines with hydrogen to make water. The perfect molecule. Water and hydrogen, hydrogen and oxygen combine. The oxygen will get to be -2 in both of these compounds. You don't have to do the oxidation numbers, but it's good practice. The hydrogen's a +1. If we figure this one out, the carbon would be, a +4. To balance those 2 oxygens, right? Now, again, these are not charges, they're oxidation states. These numbers make sense. Hydrogen is willing to take a +1. It loves being +1. That's why we show it with the metals. Oxygen, absolutely, -2 or bust. Again, I showed you a reaction where that's why it reacts when it's not. And here, this is what drives our life. All right, well, we burned a Bunsen burner. Let's do something cooler with it. So we have that other pumpkin there that my neighbor graciously gave me. And we're gonna make some bubbles. All right, he got filled up. And there we go. Bunsen burner burning. But this is the part that's really cool. Is all those bubbles are methane bubbles. In class we do it. We have a lot of fun because we usually can get them to float if the soap's just right. But there we go. Our Halloween pumpkin from my neighbor. All right, that was combustion. Lots of fun. All right, what's our next one? Is a single. So our exchange reactions. Now there's extra words that you want to ignore. So again, each of these has a second one that you get to try on your own. Come to office hours and have me check it. And then that last page, I mix them all up. So let's do the first single one together. And actually, I did do this reaction, which I will show you in a moment. All right, so our single. Sorry, I was looking for another color, so they weren't all black. We'll see how the blue shows up. Silver nitrate. So hopefully you listened to me and you made a periodic table with those handy dandy polyatomics because they come in here. Now if you want, you can show a parentheses around the NO3, and NO3 has a -1. And silver 1. Silver likes to be a 1. So silver gets a +1, and it reacts with copper. So it's just copper by itself. I actually recommend when you see them by themselves, give them their little halo. They're beautiful. All right, we're going to have to erase the diatomics just because they're getting in the way. And we're going to get a swapping happening. So remember our little mantra back when we learned how to name. Probably you don't remember it, but I did comment, and here we're going to do binary. Only 2 things coming together. So nitrate is one piece, silver is another. So you're not going to combine 3 things together. We're not going to make things where we have 2 metals. So the metals are going to switch places. We could also see ones where we have 2 nonmetals, and they will swap places. So we want to put a metal with a nonmetal. If you notice, most of what we named was ionic. They like to be metal, nonmetal. So the copper and the silver are going to switch places. So copper now goes with the nitrate, and the silver is now by itself with its halo. You can sing like the angels. All right, everybody can do the nitrate is still -1. Now, this is why we did this one together. The ones that you're going to get are going to be, that you're going to have to do by yourself, are going to be fixed charged. If you ever run into one that's in the middle, their favorite charge is +2. So they almost always go to a +2. Almost always. In this class, it's going to work. Silver is an exception. It likes to be 1. The 1As like to be 1. Aluminum likes to be a 3. That one's fixed charge. What this means, because these have different numbers, we need to put a 2 down there. We're doing this one because I found the piece of copper wire, not the piece of aluminum wire. So that subscript comes down here. That means we have 2 nitrates. So we know my error from before. So if we have 2 nitrates, this is a trick, is I'm trying to decide if I should have you all email me what my mistake was and balance it. But we should probably balance it just for the heck of it. So yeah, we'll go back to the combustion and balance it. If we were live, one of you would have already told me that. And all right, so there's 2 nitrates. See the polyatomic as a whole piece. And so we put a 2 in front of this whole thing. You can't put a 2 in the middle. You can't split apart the compound as the reactant. The copper can, but not you. So the 2 has to go in front of this whole thing. That does mean now that I doubled the silver and I doubled the nitrate, so I need another 2 over here. Now, if you want, you can leave it like this, or you can say 2, 1, 1, 2. Now, the most common question with this one is students will say, but I wrote it as silver plus copper nitrate. I balanced it correctly, so I had 2, 1, 2, 1. The order that your reactants and your products are in don't matter. It just matters that you get your compounds right and your single right. And this is called a single because an element was single and now a different element is single. What would be wrong is if you wrote the nitrate in front of the copper. So we always do metal, non-metal, cation before anion. All right, let's go back to the combustion and balance it. Balance the carbon. There's one on each side. We balance the hydrogen. There's 4 over there, so we need a 2. Cannot change the subscripts at this point. All right, now we have to do the oxygens. So we have 2 oxygens here, plus 2 more from the 2 waters. So we have 2 plus 2, which is 4. So on the other side, to get to 4, I need to put a 2. So again, you can say 1, 2, 1, 2, or you can just leave blanks instead of the ones. I really don't care. For those of you who have a different chemistry teacher eventually, I've learned most of them care. I just spend all my time caring about each of you. I really do. And so, to me, is much more important. And I want you to visually see it. And some of you, really, you need to visually have the ones there. So if you want to put blanks in front of everything and put your ones, you have infinite blessings from Leo. We're okay with that. Right, Leo? Leo says high five to them all. Because Leo would probably do that too. He says, heck yeah. All right, the last one. Let's do the demo before I forget something else. So we have some iron nitrate. And so solution just means it's dissolved in water. Remember those molarity questions we did? The molarity lab? Oh, by the way, here was this demo. And so, can you see it? So there is a copper wire. Maybe I'll just pull the copper wire out. And the copper wire now is coated with silver. And if I leave it in there long enough, we'll get lots of silver on it. We'll leave it in here until next week's lab. All right. So, let's add some sodium phosphate. Let's try to do this in front of the camera. Maybe we'll just put the camera. You guys see this exciting action? All right. Look at that. It's so exciting. There's white stuff forming. It got cloudy. Yeah, that means a solid formed. So the cloudiness, the opaqueness is that a precipitate formed. That was it. Some doubles can be more exciting, like when we make a gas. It's all a gas. All right, let's put that to the side. Let's write our reactions. Doubles end up being everyone's favorites. Again, my theory is because you start figuring out what we're doing, but they're also, as long as you put your time in and got the idea of ions and the importance of charges. All right, so iron 3 nitrate. That Roman numeral 3 means +3. Nitrate means you look at your periodic table. Yeah, nitrates show up a lot. Remember Nick the camel? He shows up a lot in these. There's a reason. Those of you who are with me in 221 will see the reason. He becomes really important in there. All right, so this 3 becomes a subscript here to balance our charges. Sodium, +1, and phosphate. Oh, another one of those. We don't need a parentheses on the phosphate, but it helps. It really helps with these exchange reactions because like up above, the nitrate just moves. In the exchange, it stays as nitrate. The only exception to that is when we have a decomposition. In decompositions, everything breaks apart and they make something all new. All right, so this time the 3 goes with the sodium. All right, now, what should we do? We're going to exchange. These are doubles. Everybody has a partner. I call them the swingers. They go in, they come out with a new partner. Arrow. Now just start with the iron, and they keep their charge. It's +3. So again, we'll show the charges up above. It will help us with the Leo Gur stuff. Leo says, yeah, right on. Now, Siren goes into the party with nitrate. Says, see you later, nitrate. Nitrate was just a ride to the party. It's like Nick in the back of the camel. Iron's now going to combine with the phosphate. So the first one goes with the last. So the PO4 comes over as a whole package, and it keeps its charge. Now, they both have the same charge, so we don't need any subscripts. All right, now we go back. Now the key here is always start with the cation. Cats come first. Sodium comes over, just one, only one. It's key. Just bring one sodium. We'll deal with the subscript by balancing with the coefficient, but you don't bring the subscript over. The exception to that is that polyatomic. The PO4 is the 4 oxygens. It's part of the polyatomic, and that's why those parentheses really rock. All right, the nitrate, you bring over the NO3, but not that subscript. But you do bring its charge, and since they both have a 1 charge, we don't need subscripts. But now we have to balance. These are easy to balance. Just go from left to right. We got 1 iron. I got 3 NO3s. So we're going to put a 3 over here. That gives me 3 sodiums, which is great. And 1 phosphate. Now you can make a list. Again, it usually takes time. So it just takes practice. So initially, if you want to do the list, you have my blessings. But try to get to a point where you don't need it all the time. But when you make your list, keep the polyatomic as a polyatomic. So you would make a list as Fe, NO3, sodium, and phosphate. But again, it takes time, and you guys have lots of other cool things you can do with your time. All right, and again, if you want to say 1, 1, 1, 3, it's fine. You can say 3 sodium nitrates plus iron phosphate. It's a double. Students love doubles. I think it's because we're going to do Leo Gur time. All right, that's why I'm dressed like Leo. Yeah, and I forgot the thing to make my whiskers. I dropped it on the way here. So I had to find charcoal, and so that's why it's not my best work of art. So, doubles. Never. We should find red. Red. Here's red. I lost my red pen. So we're just going to have to do it with the black pen. Never, ever. Red ox. You know what? Red's okay with that. So if it's a double, they're switching places. The charges stayed the same. They just switched partners. And red says, it's all right. I don't have to be everything. All the others, yes. And the key to knowing that all the others are red ox, we have halos. Right. I want to hear that in class. Like, a bunch of you come on is when I say the halo thing. That would be so fun. There we go. The ones by themselves get a halo. So we're going to do this. You don't have to do it in the lab until the last page. So with the lab, just focus on exchanging. Sorry, Leo's pants are a little big on him. Exchanging, switching, getting your products, balancing the coefficient. If you want to try and do some Leo Gur on the last page, you have to. I will look at it and give you feedback. So let's go ahead and do it. So I really would love to know what happened to my red pen. There it is. Hooray! All right, so write the acronym Leo Gur. I mean, I can't force you to do it. Everyone who does it, they get it right. So just do it. Just trust me. By now, we're like 7th, 8th week, something like that. I don't even know what week we're in. We're in November. So, Leo stands for losing electrons oxidized. And Gur, gaining electrons reduced. These guys got it. So, you're always reading the direction of the arrow from reactants to products. Oxygen's going from a 0 to a +2. It lost. And oxygen gained. I'm going to put a little X through that oxygen so you can tell it's that. All right. Let's do the whole thing. The OA and the RA, this is where they swap places. So I always write the O's first, and then I swap. So magnesium becomes the reducing agent, and O2 becomes the oxidizing agent. The agent has to be how it started out. I'm going to go back over here and do Leoger on this side because I've run out of room. This one's, we can do it. This one's a tough one. But as I said, the chromium is a +6. Now oxygen, it's always in a compound, so oxygen's a -2. Nothing happens to the oxygen, it's just rearranged. Oxygen didn't actually drive this reaction. Hydrogen, always will take the +1 for the team. It's always there. Definite team player. All right, then we got nitrogen. Nitrogen likes to be a -3 if it can, and it is. My oxidation numbers do work out. I'm not going to take the time to go through it because it has 4 pieces. In 221, we'll do some with 4. By itself, did you guys do the halo? There it is, halo. And now, there was another little trick I showed you. Leo always increases reading in the forward direction. So nitrogen's going from a -3 to a 0. So -3 means it had 3 extra electrons, and now it doesn't. So it lost them. So nitrogen is my Leo. My Ger, chromium. Its oxidation number went down as you go forward. So some people do it great with Leo Ger, and others, the arrows work. Find your method. You can do it. It takes practice, that's all. And that's what this lab is about. It gives us more practice. And the homework set, again, and then you'll be fine. You'll get it. And Leo Ger, again, this is big. This is what drives our life. Biochemistry is oxidation reactions. Illness is being over-oxidized. Eating crappy food, you're oxidizing the heck out of your body. Eating pumpkins, so many antioxidants, all the carotenoids. That's why they're so beautifully orange. And they'll fill in, and they'll make you healthy. All right, so this one for the OA and RA, the OA and RA has to be a reactant. And so this is the double agent. This is both the OA and the RA. Again, that's why I have office hours. Don't be shy. Come and see me. All right. Now, a quick comment, a reminder, combos and decomps are not always Leo Gers. The ones that we do, because we tend to do pretty straightforward ones, they probably will be, and you'll know because you'll see an element by itself. You'll see the halo. Combustions, yes, they are always Leo Ger. Always, always, because there's always oxygen by itself with its little halo. All right, so we did all the oxidation numbers. I did. Let's do these. Let's finish. So the carbon, well, hydrogen takes one for the team. Hydrogen says, I'll be the +1 if it's in a compound. There's obviously going to be exceptions. When it's by itself, it's 0. It's a halo. All right, -4 to balance. Oxidation numbers, not charges, just the potential, and we can see the carbon change big. In combustions, carbon always is going from a negative to a positive. The bigger the change, the more bang for your buck. So this is a big change. Changes in oxidation numbers are key in chemistry. It tells us the potential. We see these original numbers, but that's actually not that bad. Carbon loves to be 4, positive or negative, doesn't really care. All right, and oxygen again, this whole thing is because my GER is then my oxidizing agent, which is going to be O2, and my reducing agent. So, a couple mistakes I see students do. The agent is always a reactant. So the reducing agent is the agent that caused reduction, meaning it caused something else to gain. It was very generous. So it gave up. In that case, it loses. So that's why it's always a crisscross. I always crisscross because that's my teaching habit and it works for students. So I just put my O's on top. So you have to write as your agent the whole thing. You're going to have charts. If you look at the last page of the lab, you're going to put this all into a chart. The Leo GER is what's oxidized, what's reduced. So this is oxidized. So I'll ask you, what element? The element changes. So carbon, yeah, over on the product side, that's when it's oxidized. But I just want you to tell me the carbon was oxidized. And the oxygen, when it finally gets to be -2, it's in its reduced form. So it goes through reduction. So what happens is students can do the Leo GER, but then they can't answer my questions. So you have to be able to put it together. The other comment is I recommend doing it like how I'm doing it. Don't get lazy and do your own shortcut because you're going to keep seeing me do it this way and that will help reinforce it. Notice I always put the Leo GER, crisscross, OA, RA, that's all in the middle, and then my answers are on the outside. Because if you write the C and the O in the middle, you're going to confuse yourself. Was that the oxidizing agent or was that oxidized? Anyway, just some suggestions to help you succeed. Symbols are always Leo GERs. And they all in unison at home. You're all going, oh, right? There's always halos. So copper, so rather than saying which one was oxidized, you can just go and look. Okay, the one that's by itself, it's going from a 0 to a +2, so it's losing. It's oxidation number 1 up, and the silver went down. The NO3 is what we call a spectator. It's like you when you're watching a game. Or right now, you're not really, you're participating. You're singing along with me. It's not that the single one is always the Leo, because if we have non-metals, the game changes. But, so just figure it out. It's good practice. So we'll do, for completion, my OA is not silver. My OA is the silver nitrate. The whole reactant. And then my RA is copper, because it was just copper to start with. The products, they're just, this is cause and effect. They're there. All right. And doubles, never ever